doesn't sound bad. Okay. Who is that guy? Okay, so we're going to talk about a couple types of coverage that are most basic. And those are statement level and transition level coverage. There's two other types that are asked for in your assignment, but I think once you understand how these work, in the lab, once you understand how these work, you'll have a sense of how it generalizes. Okay? So, one of the things we're going to be looking at today for these two types of coverage is the idea of showing a graph of sort of how a program works. This is probably the first time you've seen a program delineated as a flow graph. But we can depict sort of the structure of a program as a series of nodes associated with blocks of statements on the one hand and paths between them. So up there on the left, from your vantage point, is a depiction of an if statement. So we have this if, and the body of the if, the so-called consequent, is placed in this node here. And N2 represents what? Can anyone tell me? If you kind of understand how this maps this, what does N2 represent? Anything after the if. What is this branch that's going directly from N0 to N2? What does that represent? If under the condition it's false, it just so-called falls through. There's no, talk about this being the consequent, and then if you had an else statement, that would be the alternative. There's no else statement here, so it just, if this is false, if x is greater than or equal to y, it just falls through to whatever's after this. And here, if x is less than y, it executes y. We can similarly depict a while loop in the same sort of way. So folks, this area N0 corresponds to the area just before the loop. N1 corresponds to what? Anyone? Yeah, it's this condition here. Which of these paths out represents a situation where the condition is false? Yeah, it's going to N3 here. If the condition is true, then we execute N2, this block of code associated with N2. And then we loop back to N1. Does that make sense? People? Okay. So one of the reasons I want to introduce this is it makes a convenient sort of a depiction when we talk about transitions. This is what I mean by transition. Transition between these sort of statements, for example. So we could take code like this, which is some C code. And I apologize, you folks probably can't see that from the back of the room too well, but here's a while loop, here's an if statement, else, if, and then down here is an action else. And we could take a bunch of code like that, which is pretty complicated, unnecessarily complicated in terms of everything that's presented right now. And we could turn it into a flow graph like this, okay, with kind of similar sorts of issues. So we have the depiction here is slightly different, but we have a false branch for this if this way, a true branch this way. And we could sort of draw out what was in that C code in this sort of, in a graph sort of way. We talk about this being a graph, not a graph in the sense of a chart, of something over time, but a graph in the sense that we have a set of nodes, and we have edges between those nodes that are here directly. Okay. So we could kind of map out that code in sort of pieces. And what this highlights, ladies and gentlemen, is something that's requested on your problem set, which is, it highlights something about something that's requested in the problem set, which is conditionals. So here we have a conditional, this else if, one way false, goes this way, one way true, goes that way. And one of the things you're being asked about, one of the things you're being asked about in the lab for problem 3 is the coverage. What, if, in other words, here, it's asking about, okay, for your statements, your conditionals, which it could be either true or false, how thoroughly have you evaluated them? And you can see the exact statement of what's being sought. But one way to quantify it would be the fraction of statements where you've evaluated both conditions. Another way would be said, what's the fraction of conditions you've tried? So here, for this condition, for example, we want to try the false branch, we want to try the true branch, to be confident that we've sort of captured how this works. After all, if you left out one of these, if you left out false here, you'd be at risk. We'll see that in a minute, why that might be. Okay. Generally speaking, for the coverage proposal here, we identify a set of things we need to cover. Maybe it's different outcomes for condition. Maybe it's functions that we want to cover. We want to reach different functions. That's what they also ask in your lab. And then we figure out, okay, there's a set of paths in the program that will cover those things. We want to cover every possible branch outcome. We want every if to be true on the one hand, false on the other hand. We need to take a path through the program that will lead to going down the appropriate sides of that. On one hand, false, and on the other hand, well, true. But, ladies and gentlemen, I mean, as I'm sure you appreciate, you can't just go from saying, well, I want to make it false one time and true the other. You need to say, okay, I need to create a test case which is going to sort of go down this way, and another one will go down this way. Because after all, this is not the beginning of the program. The beginning of the program is up here. And so the goal here is we have a set of things we want to cover. Maybe they're functions. Maybe they're different outcomes of a branch. We have a set of paths that go through them from the beginning. And now we need a set of test cases, specific inputs that will exercise those. So, for example, if you look here, there's a set of test cases that you would feed in as inputs to this function. This function takes two things as inputs, or two strings, char stars and C, and we need to give test inputs that will actually exercise, excuse me, I stand corrected. I retract my statement. It does take two char stars, but the second of them is actually what? Are these truly two inputs? The sentence, is it a place to put the output? It's to put the output. So it does take in two things to point to strings, but the second one is where you put the output. The first one is the one you're actually decoding. So there's some encoded string, and you're going to put the output into the so-called decoded string. So we would give it, for example, a string for encoded like test, and that would exercise some path through this program. First, it would come down here, and it would say, is the first character, so you have an E pointer assigned to encoded, so point to T. Is that character non-zero? Yeah, it's non-zero. So this while evaluates to true, so it goes this way. It says, is that first character plus character? Nah, it goes false. Is that first character a percent sign character? Nah, it goes false. In that case, what do we do here? Well, we just assign to the output the same character that was used in. It's not a special character. Nothing fancy. It doesn't need any sort of special fix. It's a character like A, or Z, or Y, or something like that you don't need to decode in some sort of special way. And then it loops back up to the top again, and it goes to the next character. So test here, if we gave this test as an input, T-E-S-T, it would go through here, and it would come down, and then it would go up like that, and it would come down and go this way, and go up like that. And it might not make that sound, although it would be entertaining if it did, but it would go this way 4 times, and then the last character would be 0, and so it would go down like that. On the other hand, if I give it something more complex, like percent sign 3D, by the way, what does that stand for, percent sign 3D? (48) 3 times 16 plus 14, right? 48 plus 14, 62. So that's what that actually stands for, character number 62 here. And asking, so here for that, it would come down here. Would it go this way or this way? We gave it percent sign 3D. When it first comes down, which way would it go? True or false? True. It would go true. In other words, there is some character that's non-zero that's pointed to. It goes this way. With the next thing, would it go true or false? Is this plus? It will go false. How about this one? True. Okay, finally, test. Did test, when we gave it test, T-E-S-T, did it reach here, ladies and gentlemen? Did it reach this block of code labeled G? When we give it T-E-S-T? No. Which ones did it reach when we give it T-E-S-T? A, B, C, D, F, L, and it kept on exercising those B, C, D, F, L several times, and then it went to M, and it was done. This time, it goes A, B, C, D, G, and then it's going to go to, actually this, it turns out to be false. You'll notice, by the way, what is this code doing? 3 times 16 plus this lower digit, and it's adding it in, and then it will go back up here, and then it will go back down. So my point is here, I don't mean to dwell on this particular example. The point is different inputs exercise different paths through the program. And if you're concerned, ladies and gentlemen, we're about reaching statements. If they were about, I want to reach these statements in block G, I want to reach these statements in block H. If you want to reach all the statements, you need different inputs. Does that make sense? You need different inputs to exercise the program so it will go different places so that you get your coverage. Now, ladies and gentlemen, if I want to be sure that every conditional was exercised to go both false and true, which is being what's requested on your lab, right? I need different inputs. One which will make it go false, perhaps, and one which will make it go true, right? Now, there's a little bit of a subtlety here, ladies and gentlemen. Because if I'm seeking, this is an important point, so pay attention. It's testable and it's significant. It bears noting and it bears a bit of mulling on your part. A given test case is a given test case gonna, let's suppose I'm concerned about hitting blocks. I'm interested in hitting statements, so I want to hit G. A given test case that I designed to hit G, I figure out, okay, how am I going to get it to hit G? Well, it needs one of these things, these percent signs, right? If I get it to hit G, is it going to hit other statements at the same time? Yes. So, because you want to hit all of A, B, C, D, E, F, G, you don't need a separate test case for each one. You may design it, your test case, oh, I want to hit G. And it turns out that same test case kind of for free. It automatically hits A, B, C, D, which are needed to get to G. Does that make sense? So it may be that we only need a quite modest set of examples to actually fully reach all statements. And in fact, ladies and gentlemen, you'll notice there's this one called T0 up there, which has 3 strings as part of it. The first is, I have to look, I think it's the empty string. And the next is TEST. The other is this long string, which includes %1 and a plus. Those collectively, those 3 strings, if you gave them the first one, and you noted what things it reached. You gave them the second one, you noted what things it reached. You gave it the third one, you notice what things it reached. Collectively, they would actually match, they would actually reach all the different possible branches within this program. It would go down, for example, the first one would go down this transition. The second one, for example, would exercise those sets. The third one would reach G. Because it also has a plus in it, it would also reach E. And so with just 3 inputs here, we can actually get it to exercise all the possible statements in this program. Does that make sense? So here, ladies and gentlemen, and I'm trying to do this in part because I'm trying to help you think through this afternoon's lab. You're going to be trying to take input that will, in some sense, force it to go the right ways for each successive if statement, for example, or will force it to reach a certain function. But you want to pay attention because that same statement, or that same input, may have gotten it to reach other functions that you weren't concerned about at that moment, but you want to record that down. And you want to record, okay, for each input, okay, what different things is it going to reach? And then you'll have a minimal set of input in some sense. A small number of inputs that will exercise, that will cover, that will achieve coverage of all the functions you want to achieve, or all of the different ways that different conditionals could go. So that was the type of English up with which I will not play. I strayed from my grammatical duties for this young generation. So I try to keep my English in proper order, but apologies for the lapse. Hanging prepositions are unfortunate. Okay, so I talked about state-based coverage here. I talked about states, but this also applies to transitions. If we are dealing with wanting to make sure we cover transitions through here, we want to go all possible transitions. You know, go left and go right here, go left and go right. It's the same basic deal in the sense that we've got to come up with test cases that will exercise this, and it often involves artfully choosing what's the input that's going to get it, say, to get down to here. Okay, we need a plus in there, so we're going to need a plus there, and to get here, we're going to need one of these percent signs, for example. And in today's lab, you're going to be exercising that sort of care. Does that make sense? Okay. Now, I could go into this in great detail, and in fact, you'll find later courses where I talk about ways of getting much more sophisticated type of coverage. Not just hitting statements, ladies and gentlemen. Not just hitting transitions, but hitting more more structured quantities that allow us to essentially get better true coverage, better confidence the program is working. We're not going to be talking about those today, but achieving all possible paths through the program is typically not possible because, as I said, a loop could go once, it could go twice, it could go 3 times, it could go hundreds of times. You don't want to test every possible one. You'll never finish testing this program. So typically, we can't cover everything, but we try to cover at least the basics. So
I'd like to talk about the most simple things, and one is the state coverage or statement coverage. And this can be undertaken at the statement level, or it can be undertaken at a high level. Suppose you have a airline ticketing system that deals with requests for tickets. And by the way, there are some international routes in which paper tickets are still given out, so there are cases where printing is still done. They're not that common, but they do exist. So here would be, for example, a case where we can diagram out an entire systems activity. You know, we make a reservation, and then we pay for the reservation. So we indicate our choices. It's temporarily reserved in our name. Then we pay for it. These are separate steps. And then we go to a state where it's ticketed, but that ticketing state can be canceled, for example, by the customer. And in fact, the customer could bomb out of the make the reservation, you know, where they're setting up the basis of the reservation. Or they can pay, but they can ask for a refund before it's been ticketed. Okay. And finally, you can have it ticketed, and then the ticket's actually used. You know, here there could be a situation where we've made the reservation, but the timer expires. We haven't actually committed to it by paying it within the requisite time, so it's canceled. So this would be a high-level system diagram that you might think has very little to do with the code. We've just been looking at star p equals such and such. But in fact, we can use similar approaches here. Here, instead of dealing with statements as the so-called nodes, we have sort of states in the system. Okay, we're in a state where the ticket reservation has been requested and made in some sense, but it isn't yet paid for. Or since we're paid for but not yet ticketed. The ticket hasn't been physically issued yet, etc. Hasn't been confirmed, etc. So here, we could use very similar reasoning, and we could say what sort of test cases, high-level cases here, do we have to exercise so it will go through all these things? Because after all, you're creating a ticketing system for people worldwide. You sure as heck need to test it such that, for example, you test the timeout. Does the timeout work? Here we're not dealing, again, with statement level concerns. We're dealing with, you know, ways that users would use the system. And you want to see, you know, if you wait 20 minutes and you've requested that thing on orbits, but you've not yet paid for it, does that thing get put back, you know, the user gets knocked out and the thing gets put back in terms of an available seat. Similarly, if you paid for it, does the cancel function work? So we can reason about testing our systems at this sort of level. And this holds for a lot of different cases. So I thought I had a case in here, but I had an ATM one where basically we're testing an ATM state. So, you know, there's a state your ATM can get in where it sucks your card in. Do you know folks know that? So at some point, if the situation is such that your card's expired, or you've entered a bad password at the automatic teller machine too many times, it just sucks it in. It takes it and it doesn't give it back to you. I've experienced that before. It didn't make that sound when it happened to me, but you know, in other cases, you can imagine that. It would be very fitting. But it just went, you know, it sucked it in. It was closer to that. So here, you know, if we had an ATM, you'd want to test, okay, does it suck the card in properly under these conditions? You know, does it time out properly? Similar sort of idea. So I don't want you to get this sense that we are dealing purely with code level stuff, that, you know, this is all what testing is about. No, folks, you do need to test at this level, particularly for more sophisticated algorithms. But you also need to test at a high level. So in case you folks don't think this goes on in reality, I know someone who did the testing at this level of all the branches in the Excel calculations to make sure that it's recalculating properly for all the things in the spreadsheet. And you do exactly this sort of thing. Reason about where the branches go, and you try to exercise it, design a clever case to get it to go this way or that way. So this is not pie in the sky stuff. This is day-to-day sort of stuff for real-life software engineering. But it doesn't just apply at the code level. It applies at the level of testing your system out. So if next year you folks are in my class 371, I'll hope that you will create, if you create a website, to, you know, maintain some information. Hopefully it's not a real-time piece ordering system, but some other sort of website. You know, I'll ask you to draw out a diagram like this and show me you've actually done testing on all these different pieces, so that I have greater confidence than you get if you were to give me 3 thumbs up. So here we can reason about sort of testing our overall functionality, and for some algorithms we'll want to dive down and sort of do this detailed testing. Okay, so let's talk at the very detailed level about state coverage. So state or statement coverage. Why it has gaps, why we might want to go beyond it. After all, we talked earlier about doing analysis on this sort of code here, so that we're sure that we've reached G, so that we're sure that we've reached H, we're sure that we've reached C, and at least some test case, because bad things can happen if we don't. Here, we might get a null pointer exception because we've assigned to D pointer, and who knows, maybe if you reach this place, it's not, it could be a null pointer. So I've talked about state coverage and wanted to cover those things. And if you don't have that, at least that, you haven't seriously tested this code. You haven't really done diligence with this. But is that enough? Is that enough? And I give this case here where it's not enough. Ladies and gentlemen, we can diagram this out using that notation we saw earlier. So here we have a situation where we can diagram an if statement. So we have a sort of some code at the top, and the if statement, one opportunity is it could just fall through to the code after it, right? Another thing it could do is it could execute the consequent and go this way. And in this case, this code before it assigns to some pointer that it's equal to null, right? C, for example. And here in the consequent, we have an assignment to p head such and such. And down here we have a indirect reference through p head to assign it some value. Sorry, folks. That's implausible. It's possible, but by convention, I shouldn't be assigning. Normally, I'm not assigning a pointer to the contents of another pointer. You can. It can be pointer to pointer, but you folks are innocent of that. I'll leave it that way for the moment. And then you call it PT, pointer to pointer. Okay. So why do I say that statement level coverage here is inadequate? Suppose I said I want to have statement level coverage. Can anyone give me a single test case here? So a single test case. So this depends on foo. If foo is greater than, if foo is equal to 0, it goes this way. If foo is not equal to 0, it goes this way. Can anyone give me a single test case that will achieve statement coverage? Single test. What does foo have to be to achieve statement coverage? Yeah, give me one. Could be 2. Yeah. Yeah. Is it anything non-zero? So in that case, what happens? It comes here. Which way does it go? Left or right? Left. And then it goes this way, right? And then it's done. Does that achieve statement coverage? Does it hit all of these things? P head equals null, P head equals this, P head equals that? Star P head equals that? Yeah? Yeah? It achieves all those things. Is this code bug-free?
Why? Exactly. Exactly. So statement coverage, we have 100% statement coverage of this code. 100% coverage. Is it bug-free? No. Why? Because statements are just the beginning point. Again, if I didn't test anything, if I had no statement coverage at all, well, we could have no confidence in it, but you can't be, you can't lend overconfidence just because you have statement coverage. So because of this, we often go to what's called transition coverage. Here we're exercising all transitions at least once. And as before, just as a given test case could reach many statements, a given test case could also cover many transitions. More than that, a given test path from beginning to end through the program would cover typically many cases and many transitions. Here, we are trying with our test cases to trigger certain transitions so that we've covered all possible transitions. So, ladies and gentlemen, if I were to label the transitions here, these are these so-called edges, these lines between these nodes, I'll label them A, B, C, D. I'd like you to give me, for this case on the board, test cases that will cover all these transitions. It'll cover A, B, C, and D. Can that be done in a single test case? No. Because either, I'll put the code back up there in case that's easier to read than my writing, or perhaps I should say because that's easier to read than my writing. So can a single test case cover all transitions here? A single pass through this? No. There's no one value of foo that will simultaneously go both drop through the code after the if statement and go through the if statement. Either foo is true or it's false. Either 0 or non-zero. And either way, we're going to do different things. Could there be two test cases? Suppose foo is the input here, the operative input. Could there be two test cases in terms of foo that would fully exercise all transitions here? If we wanted to exercise all these transitions, A, B, C, D, all of them, and we can do so across not one test case. We can't do that, but two test cases. Give me two test cases. Give me two specific values, ladies and gentlemen. This is a test case. It has to be a specific value of foo, two different specific values. One where it exercises one set of transitions, one the other set, where collectively, if you go between them, they cover all transitions. Sorry? Okay, yeah. So foo equals 1. So foo equals 1. What is what transitions are we going to trigger? Sorry? A, C, and then D, kind of for free here. Okay. And then foo equals 0. Okay. A, B, and D. Yeah. Have we collectively hit A, B, C, D? In other words, have we hit every transition at least once? Yes. So that would give us, if we're just dealing with this code, that would give us complete, those two test cases would give us complete transition coverage of this code. Would that transition coverage identify a bug that was not identified for state coverage? Yes, it would. It would, because it would identify this bug that when foo does not happen, when foo is not true, it falls through and it's on its through So transition coverage here would identify a defect that would have been lost with statement coverage. Now, you may think that this is the nature of of the pedagogic difficulty that confronts us. We don't have the time, the screen real estate, to cover real life examples in great detail. But let me assure you folks, having been someone who spent hundreds of hours debugging commercial code, does this sort of thing occur in real code, but at a more sort of a level that's less obvious? Big time. Big time. The programmer forgets to handle this odd case that can lead to a different path through the code. They forget that, it's not been initialized in this other case. They forget, to make them consistent, and it blows up. Blows up under one set of tabs and not on the other. So what I'm trying to say here, when we say coverage, you should be asking coverage of what? I've asked you in the lab to do two types of coverage. One is function coverage, make sure you've reached all functions, and that involves creating inputs, or test cases, that will get you to reach all functions. Another thing I asked you to look at was branch, condition, the test input. True and a false version. Again, those are very, very important for uncovering bugs, but they don't guarantee that all bugs will be uncovered. With this transition coverage, are there certain bugs that might not be uncovered by this? Have we succeeded, by achieving transition coverage of code, have we succeeded in making it bug-free? No. Sorry? That's right. It may be, well, even that function, it won't necessarily be bug-free, it turns out. For example, in this case, ladies and gentlemen, calc might fail. Under what is calc? Yeah, it's memory allocation. It allocates a certain number of things of a certain size. So it's how you allocate, for example, an array. It's one way to allocate an array. This code could fail. It could exhibit a bug under the condition where we run out of memory. Do you think we ever run out of memory? Yes. Oh, your innocence. Oh, God. Let me tell you about the birds and the bees, folks. We run out of memory a lot. And it's not just because the computer, it's not like your computer undergoes meltdown once every 20 years and, a cosmic ray hits it once every 100 years and weird thing happens. No, programs run out of memory a lot, not just because the whole computer does, but because that program has only been allocated a certain amount of memory, for example. It's only a certain amount of swap space available on disk. But I go into things of which you are yet innocent. So the fact is that our programs are often resource starved. And if you go into develop code for real life use by people outside of yourself, and even for people like yourself, and you count on having memory always available, it's always going to be there. You count on always having fast enough internet access. You count on the disk always having space. You will be, perhaps this will be lost to your generation, but cruising for a bruising. You'll be asking for trouble. You'll just leave yourself terribly vulnerable to bad things happening. And one of the awkwardnesses, ladies and gentlemen, of this, students don't realize it often until they're confronted with the situation. The time you most need that robustness is the time those things fail. So imagine you're creating a website to promote your product. And because someone has tweeted out a recommendation of the product. There's some person called Lady Gaga or something, and so suppose she tweets, about your product. Or suppose someone on Yelp gives a great review, whatever. They, and people hear about it, and they rush to your site. Your site's going to be under serious pressure at that moment. Lots of people hitting it. That's when you want it to shine. That's when you want it to be robust. You want to give people a good experience. You want to make sure it's responsive and quick, get back to them, and that it doesn't leave them in a situation where they're unable to function on that site. It's when you're most ready to shine that you need to be most careful about these things, or these things really come down to it. It's when your machine is pushed because people are just, making a track to your door. That's when you need to worry about memory. That's when you need to worry about threads. That's when you need to worry about disk space. That's when you need to worry about transactionality and the network being congested and so on. So being really careful about dealing with things like memory allocation, cleaning up after yourself, making sure that if calc fails, the system has some remedial action. Maybe it frees up a bunch of stuff that's rarely needed or can be swapped out or something like that. That's what will often give people that extra level of confidence or that extra level of good experience that will keep them loyal, keep your reputation good. If you're sloppy, you might think it will never matter. You might think that it will, that it's good enough, but you end up with egg on your face when you most wanted, to be able to deliver well. So here, when it comes to testing, just because we've achieved, we do want to do coverage. We want to be careful. We want to be systematic about achieving coverage and so on. And we want to do that by creating test cases like you're going to be created for the lab. But ladies and gentlemen, you further than that want to engage in what's called defensive programming. You want to be able to handle the situations which are inconvenient, which are awkward, but which are needed for your program to be reliable, or at least not do damage under very, very difficult circumstances. Okay? So don't think that coverage will get you out of the need to think about difficult situations like this. Even achieving transition coverage is only a start. And it will still leave an incumbent upon us to be able to handle sort of awkward situations where memory runs out or disk is full and what have you. Okay? So, there's many more levels that we will look at. Okay, so I think I'm going to, let me just see if there's, so with transition coverage, for example, we haven't covered combinations of situations. For example, maybe the bugging that comes up with foo is true and bar is true, foo is true and bar is not true. And we're not going to find that through transition coverage, where we're going to be going, both this way and both fall through and executing this and both fall through and executing, but not necessarily all combinations of them. Okay, I want to make one other statement though about regression testing. Okay, so a regression is when a change. So imagine you're building a program, and a change that you're making. Maybe it's adding a feature. Maybe it's changing the appearance based on user feedback, eliminating a button or whatever. You make some change, and it breaks the feature operation that previously worked, or that re-exposes the previous bug. Okay, and often this sort of failure, this so-called regression that comes about, is particularly of concern. Why is that? Why are we concerned about this sort of regression? Why is it that it's particularly of concern that a previously working set of features now fail? Why is that particularly important rather than any other sort of new set of features failing?
Because you might have coded things based on the assumption that those work, and then it's all
Good, good. So there may be dependence on those in a lot of other areas of the system, that's right. Who else might be depending on them, those features? So let me ask this, folks. So suppose you were updating some piece of software that you own. You were getting an upgrade to it. And you have two choices. Either you find that the new features that are promised in this upgrade don't all work. That's a bummer, right? You're kind of looking forward to some of these features. Some of them don't work. So you get a smaller set of features, new features that do work. Some other ones don't work. Give that as a choice versus a situation where you've upgraded and now all these things you used to count on working don't work. You've got some new features, but these things that you've been betting on working, that maybe you have documents that come from them, or ways of doing things that come from them, they don't work. Which of those is worse? The second one, because you built your habits, sometimes your documents, your data around this, and suddenly it's not working. Okay, so if we have a situation where a new feature, for example, has a failure that's detected by a user after the system's released, maybe it's user through the web, maybe it's on an app they downloaded to their Android phone, that's an embarrassment. Okay, this new thing doesn't work. But if you disrupt an existing feature, you're disrupting potentially how they do things, their customer workflow. And there's often a high cost of repair. It's ultra urgent to get this thing fixed. You start getting, desperate users because they upgraded, they expected value, and they've gotten negative value from the upgrade. Possible liability. You may have cost them business. You may have cost them, their livelihood or revenue. These things are very, very serious. Now, if we catch these things earlier, the situation is vastly better. We can fix them before exposing them to the user. But the issue is, with existing features, things that used to work, things that are for bugs that were fixed before, now suddenly they re-emerge. There's often a high cost to detect. We've got to rerun a whole lot of tests. But this is the notion of regression tests. We are testing things that are just very, very important to keep right, because often a user is counting on them. So when we're testing our program, ladies and gentlemen, it's important to test the new features, but it's often even more important, or certainly as important, to make sure the things which worked before still work. And what this leads to is a growing set of tests. When we talked about, recording tests over time, making sure we save them away and rerun them. This is one of the big motivations for doing it. You rerun the so-called regression tests. You add some new features, you got to rerun a whole swathe of tests. Some of which were because bugs fixed in the past, you want to make sure they haven't re-emerged. And others of which are just making sure the basic functionality that's always worked is still solved. Okay? So regression tests here are a key part of maintaining real software. And I want you to have this understanding that not all failed features are at the same level. Failed features that the user is counting on are ultimately likely to be more important than new features. So features the user is counting on are likely to be much more important than new features that you'd like to roll out, but for a lot of users may be icing on the cake. Okay? So I think that's all we have time for today. We're going to be going on and discussing some aspects of interfaces next time. But good luck with the lab. Good luck with the assignment. And I'll look forward to seeing you next week. We'll hope these recordings get up there. Thanks very much. Yeah. Yeah. Okay, so pardon me for just a sec. I just want to stop the recording. So